An electric arc furnace is a furnace that heats charged material by means of an electric arc. Industrial arc furnaces range in size from small units of approximately 1 ton capacity up to about 400-ton units used for secondary steelmaking. Arc furnaces used in research laboratories and by dentists may have a capacity of only a few dozen grams. Industrial electric arc furnace temperatures can be up to 1,800 degrees Celsius, while laboratory units can exceed 3,000 degrees Celsius. Arc furnaces differ from induction furnaces in that the charged material is directly exposed to an electric arc, and the current in the furnace terminals passes through the charged material. History: in the 19th century, a number of men had employed an electric arc to melt iron. Sir Humphrey Davy conducted an experimental demonstration in 1810. Welding was investigated by Pepys in 1815. Pinken attempted to create an electrothermic furnace in 1853. And, in 1878–79, Sir William Siemens took out patents for electric furnaces of the arc type. The first electric arc furnaces were developed by Paul Haar copyright Roult, of France, with a commercial plant established in the United States in 1907. The Sanderson brothers formed the Sanderson Brothers Steel Company in Syracuse, New York, installing the first electric arc furnace in the U.S. This furnace is now on display at Station Square, Pittsburgh, Pennsylvania. Initially, electric steel was a specialty product for such uses as machine tools and spring steel. Arc furnaces were also used to prepare calcium carbide for use in carbide lamps. The Stasano electric furnace is an arc-type furnace that usually rotates to mix the bath. The Girard furnace is similar to the Haar copyright Roult furnace. While EAFs were widely used in World War II for production of alloy steels, it was only later that electric steelmaking began to expand. The low capital cost for a mini-mill around $140 a $200 per ton of annual installed capacity, compared with $1,000 per ton of annual installed capacity for an integrated steel mill allowed mills to be quickly established in war-ravaged Europe, and also allowed them to successfully compete with the big United States steelmakers, such as Bethlehem Steel and U.S. Steel, for low-cost, carbon steel long products in the U.S. market. When Nucor now one of the largest steel producers in the U.S. decided to enter the long products market in 1969, they chose to start up a mini-mill, with an EAF as its steelmaking furnace, soon followed by other manufacturers. Whilst Nucor expanded rapidly in the eastern U.S., the companies that followed them into mini-mill operations concentrated on local markets for long products, where the use of an EAF allowed the plants to vary production according to local demand. This pattern was also followed globally, with EAF steel production primarily used for long products, while integrated mills, using blast furnaces and basic oxygen furnaces, cornered the markets for flat products sheet steel and heavier steel plate. In 1987, Nucor made the decision to expand into the flat products market, still using the EAF production method. Construction. An electric arc furnace used for steelmaking consists of a refractory line vessel, usually water-cooled in larger sizes, covered with a retractable roof, and through which one or more graphite electrodes enter the furnace. The furnace is primarily split into 3 sections: the shell, which consists of the side walls and lower steel bowl; the hearth, which consists of the refractory that lines the lower bowl; the roof, which may be refractory-lined or water-cooled, and can be shaped as a section of a sphere, or as a frustum. The roof also supports the refractory delta in its center, through which one or more graphite electrodes enter. The hearth may be hemispherical in shape, or in an eccentric bottom-tapping furnace, the hearth has the shape of a halved egg. In modern melt shops, the furnace is often raised off the ground floor, so that ladles and slag pots can easily be maneuvered under either end of the furnace. Separate from the furnace structure is the electrode support and electrical system, and the tilting platform on which the furnace rests. 2 configurations are possible: the electrode supports and the roof tilt with the furnace, or are fixed to the raised platform. A typical alternating current furnace is powered by a 3-phase electrical supply and therefore has 3 electrodes. Electrodes are round in section, and typically in segments with threaded couplings, so that as the electrodes wear, new segments can be added. The arc forms between the charged material and the electrode. The charge is heated both by current passing through the charge and by the radiant energy evolved by the arc. The electrodes are automatically raised and lowered by a positioning system, which may use either electric winch hoists or hydraulic cylinders. The regulating system maintains approximately constant current and power input during the melting of the charge, even though scrap may move under the electrodes as it melts. The mast arms holding the electrodes can either carry heavy bush bars or be hot arms, where the whole arm carries the current, increasing efficiency. Hot arms can be made from copper-clad steel or aluminium. Since the electrodes move up and down automatically for regulation of the arc, and are raised to allow removal of the furnace roof, large water-cooled cables connect the bus tube's arms with a transformer located adjacent to the furnace. To protect the transformer from heat, it is installed in a vault and is itself cooled via pumped oil exchanging heat with the plant's water cooling systems, as the electrical conditions for arc furnace steelmaking are extremely stressful on the transformer. The furnace is built on a tilting platform so that the liquid steel can be poured into another vessel for transport. The operation of tilting the furnace to pour molten steel is called tapping. Originally, all steelmaking furnaces had a tapping spout closed with refractory that washed out when the furnace was tilted, but often modern furnaces have an eccentric bottom tap hole to reduce inclusion of nitrogen and slag in the liquid steel. These furnaces have a tap hole that passes vertically through the hearth and shell, and is set off-center in the narrow nose of the egg-shaped half. It is filled with refractory sand, such as olivine, when it is closed off. Modern plants may have two shells with a single set of electrodes that can be transferred between the two. One shell preheats scrap while the other shell is utilized for meltdown. Other DC-based furnaces have a similar arrangement, but have electrodes for each shell and one set of electronics. AC furnaces usually exhibit a pattern of hot and cold spots around the hearth perimeter, with the cold spots located between the electrodes. Modern furnaces mount oxygen fuel burners in the side wall and use them to provide chemical energy to the cold spots, making the heating of the steel more uniform. Additional chemical energy is provided by injecting oxygen and carbon into the furnace. Historically this was done through lances in the slag door, now this is mainly done through multiple wall-mounted injection units that combine the oxygen fuel burners and the oxygen or carbon injection systems into one unit. A mid-size modern steelmaking furnace would have a transformer rated about 60 million volt-amperes, with a secondary voltage between 400 and 900 volts and a secondary current in excess of 44,000 amperes. In a modern shop such a furnace would be expected to produce a quantity of 80 metric tons of liquid steel in approximately 50 minutes from charging with cold scrap to tapping the furnace. In comparison, basic oxygen furnaces can have a capacity of 150-300 tons per batch, or heat, and can produce a heat in 30-40 minutes. Enormous variations exist in furnace design details and operation, depending on the end product and local conditions, as well as ongoing research to improve furnace efficiency. The largest scrap-only furnace is a DC furnace operated by Tokyo Steel in Japan, with a tap weight of 420 metric tons and fed by 832 MVA transformers for 256 MVA total power. To produce a ton of steel in an electric arc furnace requires approximately 400 kWh per short ton or about 440 kWh per metric ton. The theoretical minimum amount of energy required to melt a ton of scrap steel is 300 kWh. Therefore, a 300-ton, 300 MVA EAF will require approximately 132 MWh of energy to melt the steel, and a power-on time of approximately 37 minutes. Electric arc steelmaking is only economical where there is plentiful electricity, with a well-developed electrical grid. In many locations, mills operate during off-peak hours when utilities have surplus power generating capacity and the price of electricity is less. Operation: scrap metal is delivered to a scrap bay, located next to the melt shop. Scrap generally comes in two main grades, shred and heavy melt. along with some direct reduced iron or pig iron for chemical balance. Some furnaces melt almost 100% DRI. The scrap is loaded into large buckets called baskets, with clamshell doors for a base. Care is taken to layer the scrap in the basket to ensure good furnace operation. Heavy melt is placed on top of a light layer of protective shred, on top of which is placed more shred. These layers should be present in the furnace after charging. After loading, the basket may pass to a scrap preheater, which uses hot furnace off gases to heat the scrap and recover energy, increasing plant efficiency. The scrap basket is then taken to the melt shop, the roof is swung off the furnace, and the furnace is charged with scrap from the basket. Charging is one of the more dangerous operations for the EAF operators. A lot of potential energy is released by multiple tons of falling metal. Any liquid metal in the furnace is often displaced upwards and outwards by the solid scrap, and the grease and dust on the scrap is ignited if the furnace is hot, resulting in a fireball erupting. In some twin-shell furnaces, the scrap is charged into the second shell while the first is being melted down, and preheated with off-gas from the active shell. Other operations are continuous charging preheating scrap on a conveyor belt, which then discharges the scrap into the furnace proper, or charging the scrap from a shaft set above the furnace, with off-gases directed through the shaft. Other furnaces can be charged with hot metal from other operations. After charging, the roof is swung back over the furnace and meltdown commences. The electrodes are lowered onto the scrap, an arc is struck and the electrodes are then set to bore into the layer of shred at the top of the furnace. Lower voltages are selected for this first part of the operation to protect the roof and walls from excessive heat and damage from the arcs. Once the electrodes have reached the heavy melt at the base of the furnace and the arcs are shielded by the scrap, the voltage can be increased and the electrodes raised slightly, lengthening the arcs and increasing power to the melt. This enables a molten pool to form more rapidly, reducing tap-to-tap times. Oxygen is blown into the scrap, combusting or cutting the steel, and extra chemical heat is provided by wall-mounted oxygen fuel burners. Both processes accelerate scrap meltdown. Supersonic nozzles enable oxygen jets to penetrate foaming slag and reach the liquid bath. An important part of steelmaking is the formation of slag, which floats on the surface of the molten steel. Slag usually consists of metal oxides, and acts as a destination for oxidized impurities, as a thermal blanket and helping to reduce erosion of the refractory lining. For a furnace with basic refractories, which includes most carbon steel-producing furnaces, the usual slag formers are calcium oxide and magnesium oxide. These slag formers are either charged with a scrap, or blown into the furnace during meltdown. Another major component of EAF slag is iron oxide from steel combusting with the injected oxygen. Later in the heat, carbon is injected into this slag layer, reacting with the iron oxide to form metallic iron and carbon monoxide gas, which then causes the slag to foam, allowing greater thermal efficiency, and better arc stability and electrical efficiency. The slag blanket also covers the arcs, preventing damage to the furnace roof and side walls from radiant heat. Once the scrap has completely melted down and a flat bath is reached, another bucket of scrap can be charged into the furnace and melted down, although EAF development is moving towards single-charge designs. After the second charge is completely melted, refining operations take place to check and correct the steel chemistry and superheat the melt above its freezing temperature in preparation for tapping. More slag formers are introduced and more oxygen is blown into the bath, burning out impurities such as silicon, sulfur, phosphorus, aluminium, manganese, and calcium, and removing their oxides to the slag. Removal of carbon takes place after these elements are burnt out first, as they have a greater affinity for oxygen. Metals that have a poorer affinity for oxygen than iron, such as nickel and copper, cannot be removed through oxidation and must be controlled through scrap chemistry alone, such as introducing the direct reduced iron and pig iron mentioned earlier. A foaming slag is maintained throughout, and often overflows the furnace to pour out of the slag door into the slag pit. Temperature sampling and chemical sampling take place via an automatic lances. Oxygen and carbon can be automatically measured via special probes that dip into the steel, but for all other elements, A chill sample a small, solidified sample of the steel was analyzed on an arc emission spectrometer. Once the temperature and chemistry are correct, the steel is tapped out into a preheated ladle through tilting the furnace. For plain carbon steel furnaces, as soon as slag is detected during tapping, the furnace is rapidly tilted back towards the deslagging side, minimizing slag carryover into the ladle. For some special steel grades, including stainless steel, the slag is poured into the ladle as well, to be treated at the ladle furnace to recover valuable alloying elements. During tapping, some alloy additions are introduced in the metal stream, and more lime is added on top of the ladle to begin building a new slag layer. Often, a few tons of liquid steel and slag is left in the furnace in order to form a hot eel, which helps preheat the next charge of scrap and accelerate its meltdown. During and after tapping, the furnace is turned around, the slag door is cleaned of solidified slag, repairs may take place, and electrodes are inspected for damage or lengthened through the addition of new segments. The tap hole is filled with sand at the completion of tapping. For a 90-ton, medium-power furnace, the whole process will usually take about 60–70 minutes from the tapping of one heat to the tapping of the next. Advantages of electric arc furnace for steelmaking: the use of EAFs allows steel to be made from a 100% scrap metal feedstock. This greatly reduces the energy required to make steel when compared with primary steelmaking from ores. Another benefit is flexibility. While blast furnaces cannot vary their production by much and can remain in operation for years at a time, EAFs can be rapidly started and stopped, allowing the steel mill to vary production according to demand. Although steelmaking arc furnaces generally use scrap steel as their primary feedstock, if hot metal from a blast furnace or direct reduced iron is available economically, these can also be used as furnace feed. As EAFs require large quantities of electrical power, many companies schedule their operations to take advantage of off-peak electricity pricing. A typical steelmaking arc furnace is the source of steel for a mini-mill, which may make bars or strip product. Mini-mills can be sited relatively near to the markets for steel products, and the transport requirements are less than for an integrated mill, which would commonly be sited near a harbor for access to shipping. Environmental issues: although the modern electric arc furnace is a highly efficient recycler of steel scrap, operation of an arc furnace shop can have adverse environmental effects. Much of the capital cost of a new installation will be devoted to systems intended to reduce these effects, which include enclosures to reduce high sound levels, dust collector for furnace off-gas, slag production, cooling water demand, heavy truck traffic for scrap, materials handling, and product. Environmental effects of electricity generation: because of the very dynamic quality of the arc furnace load, power systems may require technical measures to maintain the quality of power for other customers. Flicker and harmonic distortion are common side effects of arc furnace operation on a power system. Other electric arc furnaces. For steelmaking, direct current arc furnaces are used, with a single electrode in the roof and the current returned through a conductive bottom lining or conductive pins in the base. The advantage of DC is lower electrode consumption per ton of steel produced, since only one electrode is used, as well as less electrical harmonics and other similar problems. The size of DC arc furnaces is limited by the current carrying capacity of available electrodes, and the maximum allowable voltage. Maintenance of the conductive furnace hearth is a bottleneck in extended operation of a DC arc furnace. In a steel plant, a ladle furnace is used to maintain the temperature of liquid steel during processing after tapping from EAF or to change the alloy composition. The ladle is used for the first purpose when there is a delay later in the steelmaking process. The ladle furnace consists of a refractory roof, a heating system, and, when applicable, a provision for injecting argon gas into the bottom of the melt for stirring. Unlike a scrap melting furnace, a ladle furnace does not have a tilting or scrap charging mechanism. Electric arc furnaces are also used for production of calcium carbide, ferroalloys and other non-ferrous alloys, and for production of phosphorus. Furnaces for these services are physically different from steel-making furnaces and may operate on a continuous, rather than batch, basis. Continuous process furnaces may also use paste-type, Zarderberg electrodes to prevent interruptions due to electrode changes. Such a furnace is known as a submerged arc furnace because the electrode tips are buried in the slag charge, and arcing occurs through the slag, between the mat and the electrode. A steelmaking arc furnace, by comparison, arcs in the open. The key is the electrical resistance, which is what generates the heat required. The resistance in a steelmaking furnace is the atmosphere, while in a submerged arc furnace the slag or charge forms the resistance. The liquid metal formed in either furnace is too conductive to form an effective heat-generating resistance. Amateurs have constructed a variety of arc furnaces, often based on electric arc welding kits contained bicyclical blocks or flower pots. Though crude, these simple furnaces can melt a wide range of materials, create calcium carbide, etc. Electric arcade furnace cooling methods. Non-pressurized water cooling. This process, also called spray cooling, performs its cooling function at atmospheric pressure utilizing spray nozzles to supply cooling water to roofs, sidewalls and off-gas ductwork on electric arc furnaces. Each nozzle is located and sized to provide the required amount of cooling water for the varying heat loads through the equipment. Spray nozzles provide uniform turbulence across the hot phase, providing an efficient cooling method. This technology was developed as a safer alternative by steelmakers and patented by Union Carbide Corporation. System Spray Cooled Incorporated later purchased this patented cooling technology, a member of the Systems Group. Plasma arc furnace. A plasma arc furnace uses plasma torches instead of graphite electrodes. Each of these torches consists of a casing provided with a nozzle and an axial tubing for feeding a plasma-forming gas, and a burnable cylindrical graphite electrode located within the tubing. Such furnaces can be referred to as PAM furnaces. They are used extensively in the titanium melt industry and similar specialty metals industries. Vacuum arc remelting. Vacuum arc remelting is a secondary remelting process for vacuum refining and manufacturing of ingots with improved chemical and mechanical homogeneity. In critical military and commercial aerospace applications, material engineers commonly specify VIM/VAR steels. VIM means vacuum induction melted and VAR means vacuum arcade remelted. VIM/VAR steels become bearings for jet engines, rotor shafts for military helicopters, flap actuators for fighter jets, gears in jet or helicopter transmissions, mounts or fasteners for jet engines, jet tail hooks and other demanding applications. Most grades of steel are melted once and are then cast or teamed into a solid form prior to extensive forging or rolling to a metallurgically sound form. In contrast, VIM/VAR steels go through two more highly purifying melts under vacuum. After melting in an electric arc furnace and alloying in an argon-oxygen decarburization vessel, steels destined for vacuum remelting are cast into ingot molds. The solidified ingots then head for a vacuum induction melting furnace. This vacuum remelting process rids the steel of inclusions and unwanted gases while optimizing the chemical composition. The VIM operation returns these solid ingots to the molten state in the contaminant-free void of a vacuum. This tightly controlled melt often requires up to 24 hours. Still enveloped by the vacuum, the hot metal flows from the VIM furnace crucible into giant electrode molds. A typical electrode stands about 15 feet tall and will be in various diameters. The electrodes solidify under vacuum. For VIM/VAR steels, the surface of the cooled electrodes must be ground to remove surface irregularities and impurities before the next vacuum remelt. Then the ground electrode is placed in a VAR furnace. In a VAR furnace, the steel gradually melts drop by drop in the vacuum-sealed chamber. Vacuum arc remelting further removes lingering inclusions to provide superior steel cleanliness and further remove gases such as oxygen, nitrogen and hydrogen. Controlling the rate at which these droplets form and solidify ensures a consistency of chemistry and microstructure throughout the entire VIM/VAR ingot. This in turn makes the steel more resistant to fracture or fatigue. This refinement process is essential to meet the performance characteristics of parts like a helicopter rotor shaft, a flap actuator on a military jet or a bearing in a jet engine. For some commercial or military applications, steel alloys may go through only one vacuum remold, namely the VAR. For example, steels for solid rocket cases, landing gears or torsion bars for fighting vehicles typically involve the one vacuum remold. Vacuum arc remelting is also used in production of titanium and other metals which are reactive or in which high purity is required. See also: Flid-in process. References. Further reading: J.A.T. Jones, B. Bowman, P.A. LaFranc, Electric Furnace Steelmaking, In the Making, Shaping and Treating of Steel, R.J. Fruian, Editor. 1998, The AISE Steel Foundation, Pittsburgh. Pages 525–660. Thomas Comerford Martin and Stephen Leidy-Coles, The Story of Electricity, New York, 1919, No ISBN, Chapter 13 The Electric Furnace, available on the Internet Archive. External links: recognition of first foundry as historical site, homemade small-scale arc furnace using a welder, electric arcade furnace module at steeluniversity.org, including a fully interactive simulation. Process models demonstrate the EAF operation and control. YouTube video of a small EAF in New Zealand, EAF non-pressurized cooling technology.